Hi and welcome. In this video, we're going to discuss the conceptual way that we can find arc length using integrals. So we've been using integrals so far to find areas under curves and areas between curves, but we can also use integrals to help us find the lengths of curves. In this video, I'll just be setting up the formula and explaining the concepts behind how it works, and I'll do the examples in a different video. As a note, the word arc length just means the length of a curve. So for us, this is just another way of saying the length of a curve. Saying arc length is just a little bit of a shorter way to do that. All right, so let's set up our arc length situation and figure out how we can use an integral to help us out. So if I have some curve here on my graph, let's say it's f of x, and I want to look at an interval of this curve, so from a to b, and find the length of the curve on this interval. So I'm trying to find this whole length, and I want to know just like what's the distance from a to b along my curve. What we can do here is use the idea that an integral is an infinite sum by finding a bunch of little small segments of the curve and adding them all up. So we're going to take a little infinitely small interval dx and find the length of that little piece and then repeat. So add them all up from a to b. That's our general concept. We're going to take these little pieces and add them all up, but how we do that's going to require a little bit of work. So let me show you what we're going to do. I'm going to just blow up a section of the graph and sort of zoom in on it. So if we have this little piece of our function, this length that we're trying to find, we can think of this as a triangle actually, and use some of what we know with triangles to help us out. So the way I've set this up, the horizontal part of the triangle, so that base of the triangle, has a length of dx, so there's some really infinitely small little width dx, and then it has a height of our triangle of dy, so some really little small height dy. So we're taking this tiny little itty bitty triangle and we're going to use what we know about triangles to find this length. So what we're going to do in this case is use Pythagorean theorem. Here we can say that the length of this little segment, squared, is equal to the square of the sides added together. So dx squared plus dy squared. Now remember, we're trying to find a formula for the length so that we can do an integral to add them all up. So I'm going to take the square root of both sides and then have a formula for my length. So length is equal to the square root of dx squared plus dy squared. Alright, so this is cool and all, we have a formula for the length, but it doesn't really have anything to do with our problem. So far we haven't used our function f of x in any way. So we're going to do some manipulating of this equation to try to make it look more useful to us, and we want it to rely somehow on the actual function that we're trying to find the arc length of. Since I know what the formula needs to be, I kind of know how we're going to do this manipulation, but hopefully you can imagine that if you sat down and worked really hard on this for a long time, maybe you'd eventually come up with this particular way to simplify this. It's going to seem like I kind of pulled it out of thin air, but it's just because I know where we're heading. So what we're going to do first is factor out a dx squared. Eventually this dx squared and the square root are going to cancel, and we're going to be left with just a dx, which is good since we need that dx as part of our integral, but you'll see that later. So okay, we're factoring out this dx squared, and now we need to figure out what we're left with. So if I take dx squared out of the first term, I'm just left with 1. And then in the second term, we're going to think about dividing by that dx squared as part of factoring it out. So I have plus a dy squared divided by dx squared. And then something you can do if this doesn't seem super intuitive is think about distributing the dx squared back in, and you should see that it appropriately cancels. So the dx squared times 1 gives us that first dx squared, and then when you distribute it to the second term, it will cancel with the dx squared in the denominator, and you're left with the dy squared. Okay, we factored out the dx squared. Now I'm just going to do some simplifying. So looking at the dy squared divided by dx squared, I'm going to rewrite that as dy over dx squared. Now, this is good because we can do something with this dy dx. Since our function is f of x, that's like a y equals f of x, what this actually represents is f prime of x, the derivative of our function f. And that's because y is equal to f of x. We input x into the function and it gives us out a y. So y equals f of x. Then dy dx would be the derivative with respect to x of our function. Okay, so we're making progress. We've now incorporated our function f of x in some way, so let's write this out. I'm going to separate the square root into a product of square roots. So I have the square root of dx squared times the square root of what's left over, so 1 plus f prime of x squared. And then we will just do some simplifying with the square root and the squared on the dx. So I have dx times the square root of 1 plus f prime of x squared. And now we have a formula for the length of one infinitely small piece of the curve. So we've got a little piece of the curve. This is the formula for the length of just that one little piece, and we'll use an integral to add them all up. Okay, so we're almost there. We're going to sum up all of these lengths by using an integral. So we'll take the integral from a to b, that's the interval we're looking on, of the square root of 1 plus f prime of x squared dx. And there we go. That's the length of our function f of x, of our curve, from a to b. So in practice, we just use this formula when we're asked to find the arc length, but I think it's nice to at least have seen a little bit behind the scenes of how someone came up with this formula and where it came from. Otherwise, it can just seem totally random that there's a square root and a squared and a derivative is just sort of there, and it's like, where did that come from? But seeing the Pythagorean theorem and how we maybe got here can hopefully provide a little bit of insight to you as to why this formula is the way it is and why it works. Alright, that's it for this one. Thanks so much for watching, and I will talk to you in the next one.